Have you ever noticed that everything in the universe, from atoms to galaxies, is spinning? The Earth turns on its axis, the Moon orbits us, and the Milky Way itself swirls through space. But why does everything keep spinning? Why isn't the universe still? So, if you want to know the answer to that question, watch this video till the end and subscribe to the channel. Let's begin. When scientists talk about something spinning, they're referring to a few different but related kinds of motion. The most familiar one is rotation, when an object turns around an internal line called its axis. The Earth, for example, rotates once every 24 hours around an imaginary axis that runs from the North Pole to the South Pole. This rotation gives us day and night. A spinning basketball or a rotating wheel follows the same principle. It turns around itself. But there's also revolution, or orbiting, which is when one object moves around another. The Moon orbits Earth, and Earth orbits the Sun. In this case, the object isn't spinning around its own center, though it might do that too, but moving in a curved path through space under the influence of gravity. That's a different kind of spin, though people often use the word casually for both. Then there's a deeper, more mysterious kind of spin, intrinsic spin, a property of subatomic particles like electrons, protons, and neutrons. This isn't rotation in the normal sense. It's not as if the particle is physically turning. Instead, it's a built-in form of angular momentum, a quantum property that has no true analog in our everyday world. Electrons, for instance, have spin values of +1/2 or -1/2, which determine how they behave in magnetic fields and how they form the structure of atoms. In quantum physics, spin is as fundamental as mass or charge. It's simply part of what makes a particle what it is. So when we say everything in the universe spins, we're talking about motion at every scale, from the mechanical twirl of planets and stars to the quantum level spin that defines matter itself. Spin isn't just a movement, it's a fundamental expression of how the universe organizes itself. You don't have to look deep into space to see spinning in action. It's all around us, shaping our daily lives in ways we rarely notice. Every 24 hours, the Earth completes one full rotation on its axis, carrying us smoothly from sunrise to sunset. That steady spin gives us day and night, the rhythm of time that life on our planet has evolved to follow. Look up at the sky, and you'll see the Moon tracing a circular path around us, its orbit perfectly balanced by the pull of Earth's gravity. Together, these motions create the familiar dance of tides rising and falling across our oceans. Here on Earth, spinning shows up in smaller, tangible ways too. A spinning top wobbles but stays upright as it turns, thanks to angular momentum, the same principle that keeps planets stable in their orbits. When a figure skater pulls in their arms and twirls faster, that's the same law of motion that causes collapsing gas clouds in space to spin faster as they form stars. Even the swirling fury of a tornado or the spiraling pattern of a hurricane reflects nature's tendency toward rotation. These storms form as warm, moist air rises and twists under the influence of Earth's rotation, creating powerful rotating systems that mirror the same forces shaping galaxies billions of light years away. From a breeze turning into a storm to planets spinning in the void, the same invisible rule ties it all together. Spin is not an isolated event. It's a universal pattern, repeating itself across every scale of existence, reminding us that the laws governing the cosmos are the same ones at play in the world right beneath our feet. At the heart of all this spinning, whether it's a galaxy turning majestically in space or a simple coin spinning on a table, lies one of the most profound principles in all of physics: angular momentum. This concept is the key to understanding why everything in the universe keeps spinning, and why once something begins rotating, it tends to stay that way unless something interferes. Angular momentum isn't just a mathematical curiosity. It's one of the fundamental quantities that nature always preserves, woven into the very fabric of motion itself. To grasp what angular momentum truly means, imagine pushing a merry-go-round at a playground. As you give it a push, it starts to rotate. The faster you push, the faster it spins. And once it's moving, it doesn't just stop on its own. You can slow it down with friction, say by dragging your feet against the ground. But unless some external force interferes, it keeps rotating. That stubborn persistence of motion is angular momentum in action. It's the rotational cousin of linear momentum, which describes how objects in motion tend to stay in motion. While linear momentum applies to things moving in straight lines, angular momentum governs things that turn, rotate, or revolve. In physics, angular momentum depends on three main things: how massive something is, how fast it's spinning, and how its mass is distributed relative to its axis of rotation. For instance, a figure skater who stretches her arms out spins slower, but as she pulls them in close, she spins faster. This isn't magic, it's the conservation of angular momentum. By bringing her mass closer to her center, she reduces her rotational radius, and since angular momentum must stay constant, her speed increases. It's a perfect demonstration of how nature keeps its books balanced. If one part of the equation changes, another must adjust to compensate. This principle applies far beyond ice rinks and playgrounds. It governs the motion of planets, stars, and galaxies. When a massive cloud of gas and dust begins to collapse under its own gravity in space, even the slightest initial rotation, no matter how faint, gets amplified. As the cloud shrinks, its spin increases dramatically, just as the skater spins faster when she pulls her arms in. This is why newly formed stars, born from collapsing clouds of matter, are almost always rotating rapidly. Angular momentum doesn't allow the spin to simply vanish. It must be conserved, redistributed, or transformed. The beauty of angular momentum is that it explains not only motion, but stability. A spinning top remains upright because its angular momentum resists changes to its orientation. Similarly, the Earth's rotation stabilizes its axis, preventing it from tumbling unpredictably through space. This stability is crucial for maintaining our planet's climate and seasons. Without that consistent spin, the delicate balance of life-supporting conditions we depend on would not exist. On the cosmic scale, angular momentum is everywhere. Every planet in our solar system spins, most of them orbit in the same direction, and even the Sun itself is rotating. This is not coincidence. It's a direct consequence of the conservation of angular momentum that began in the earliest moments of the universe. The same law that keeps a spinning top upright also governs the graceful, ordered motion of celestial bodies across billions of light years. Even galaxies themselves are subject to this rule. When the first matter in the early universe began to clump together under gravity, tiny variations in density caused some regions to rotate slightly. Over billions of years, these rotations intensified, giving rise to the vast spiral galaxies we see today, whirling collections of billions of stars, each one obeying the same ancient law. The Milky Way, for example, spins once every 225 million years, carrying our entire solar system along with it on this colossal journey. But angular momentum doesn't just apply to visible, tangible objects. It's a universal constant of motion, one of nature's most sacred symmetries. Physicists often describe conservation laws as inviolable, meaning they can't be broken. They arise from deep symmetries in the structure of reality itself. In fact, the conservation of angular momentum is a direct result of a concept known as rotational symmetry. The idea that the laws of physics remain the same no matter how you rotate your frame of reference. This principle is embedded so deeply in the universe that it shapes everything from the path of orbiting moons to the spin of subatomic particles. Consider also how angular momentum interacts with energy. When a spinning object loses angular momentum, through friction, radiation, or interaction with another object. That lost momentum doesn't just disappear, it gets transferred. A slowing planet might pass some of its angular momentum to its orbiting moons or to tidal forces in its atmosphere. A collapsing star might eject part of its mass outward in a massive burst, carrying away excess spin. Even the merging of galaxies redistributes angular momentum between their stars and dark matter halos. The universe, it seems, is constantly managing its spinning assets, redistributing motion in a grand, eternal balancing act. If you've ever watched a tornado form, you've seen angular momentum at work in real time. Warm air rises, cool air descends, and a small rotational twist begins, perhaps caused by differences in wind speed or direction. As the rotating air column tightens, it spins faster and faster, forming a vortex that can tear through the landscape with devastating force. The same principle applies to hurricanes, whirlpools, and even the formation of solar systems. In each case, nature takes a tiny seed of rotation and amplifies it through the conservation of angular momentum. To understand why everything in the universe spins, we have to journey all the way back to the very beginning of time itself, to the moment of the Big Bang. Around 13.8 billion years ago, everything that exists today, every star, every atom, every galaxy, was once compressed into an unimaginably hot, dense point. Then, in a fraction of a second, that singularity expanded outward in a burst of energy so immense that space, time, and matter were all born together. The Big Bang wasn't an explosion in space. It was the expansion of space itself, stretching outward, carrying energy and matter along for the ride. At first glance, it might seem that the Big Bang should have created a perfectly uniform universe, one without any preferred direction of motion. No up, down, left, or right. If everything expanded evenly, you'd expect all motion to balance out, leading to stillness once the initial expansion smoothed out. But that's not what happened. Instead, our universe is full of structure, stars, galaxies, clusters, cosmic filaments, and all of them are spinning. The reason for this lies in something wonderfully imperfect, the slight unevenness in the early universe. When the universe was just seconds old, it was filled with a hot, dense soup of particles and radiation. Even then, there were tiny fluctuations, minuscule differences in density and temperature across different regions of space. These weren't random accidents. They were quantum fluctuations, tiny ripples in the energy field left over from the earliest moments of existence. Over time, gravity amplified these ripples, pulling slightly denser regions into clumps that would eventually form galaxies, stars, and planets. Now, imagine those clumps in their earliest stages. If any tiny region of matter had even the smallest bit of irregular motion, perhaps one side was just slightly denser or moving a little faster than another, that imbalance would introduce a tiny amount of spin. As gravity drew the matter together, this minuscule rotation grew stronger. The same principle that makes a figure skater spin faster when she pulls her arms inward applied here too. As matter contracted, it began to spin faster and faster. Those microscopic asymmetries in the primordial plasma became the seeds of cosmic rotation. The Big Bang, then, didn't just create matter and energy, it created motion. The expansion of the universe wasn't a smooth, symmetrical event. It was dynamic and turbulent. Space itself expanded unevenly, leaving behind small variations in density and velocity. These imperfections, so small that they can be measured today as tiny temperature differences in the cosmic microwave background radiation, were enough to set everything spinning. Without those tiny flaws, there might never have been any galaxies, stars, or planets at all. It's also important to note that angular momentum didn't have to appear out of nowhere during the Big Bang. It was inherent in the dynamics of that expansion. The total angular momentum of the universe might even sum to zero when considering all directions, but locally, pockets of matter could still acquire rotation. Some regions spun one way, others the opposite way, balancing out on the grander scales while still allowing individual galaxies and systems to rotate. That's why some galaxies spin clockwise, while others spin counterclockwise. There's no universal direction to the cosmic dance, only local variations born from those ancient ripples. The Big Bang was not chaos, it was organized energy unfolding. And in that unfolding, spin was an inevitable outcome. Once matter began to condense, every particle, every atom, every cloud of dust inherited the motion of that primordial expansion. Over billions of years, those motions evolved into the swirling galaxies, orbiting planets, and rotating stars we see today. In a very real sense, every rotation in the cosmos is a faint echo of that first moment, the afterglow of creation's initial push. When astronomers look deep into the cosmic microwave background, the faint radiation left over from the Big Bang, they see evidence of this early motion. Those tiny fluctuations, 1 part in 100,000, are like fingerprints of the universe's first movements. Without them, there would have been no gravitational clumping, no angular momentum to amplify, and no spinning stars to light the sky. The Big Bang didn't just set the universe expanding, it set it turning. This is perhaps one of the most poetic truths in cosmology. The very imperfections in the universe's birth, the faint asymmetries in that first great expansion, became the foundation for everything we now see. Every planet's spin, every orbit, every galaxy's graceful rotation traces back to those ancient irregularities. If the Big Bang had been perfectly smooth, we would live in a featureless, motionless universe, cold, empty, and still. Instead, because it was just slightly uneven, we exist in a cosmos alive with motion, energy, and spin. So, the next time you look up at the stars and watch them trace their slow arcs across the night sky, remember that their motion isn't random. It's a story written 13.8 billion years ago, in the first instant of time itself. The Big Bang set the universe spinning, and we are still caught in that eternal whirl, every atom of our bodies carrying the ancient momentum of creation's first breath. After the Big Bang flooded the cosmos with energy and matter, the universe began to expand and cool. As it did, something extraordinary started to happen. Tiny fluctuations in density left over from that first explosive moment began to grow. Some regions of space were just slightly denser than others, and these small differences allowed gravity, the great sculptor of the cosmos, to get to work. Over millions of years, gravity began pulling matter together, forming the first cosmic clumps. This process, known as cosmic clumping, was the beginning of structure, the slow and majestic transformation of chaos into order. At first, the universe was a vast sea of hydrogen and helium gas, spread out across space like a fine mist. There were no stars, no galaxies, just diffuse clouds of atoms. But gravity is patient and relentless. Wherever there was a slightly higher concentration of matter, its gravitational pull became a little stronger, drawing in nearby material. As that region grew denser, its gravitational pull intensified even more, creating a feedback loop. Dense regions got denser, and empty regions got emptier. This process led to the formation of vast cosmic webs, great filaments and knots of matter stretching across the universe, the scaffolding on which galaxies would eventually form. But here's where spin enters the picture again. As these clouds of gas and dust were pulled inward by gravity, they didn't collapse straight down into perfect stillness. They almost always had some small, random motion to begin with, tiny swirls and eddies left over from those early irregularities in the Big Bang. As gravity compressed these clouds, their rotation became more pronounced. Just like a figure skater pulling in their arms to spin faster, a collapsing gas cloud speeds up as it shrinks. This is the conservation of angular momentum in action. As the size of the rotating cloud decreases, its spin rate must increase to keep its total angular momentum constant. Imagine an enormous cloud of gas, light years across, slowly collapsing under its own gravity. At first, its rotation is so subtle that it's almost undetectable. But as the cloud pulls inward, it starts to flatten out into a disk shape, spinning faster and faster around a central axis. This transformation, from a spherical cloud to a flattened, rotating disk, is one of the defining moments in the birth of stars and planetary systems. It's the natural outcome of cosmic clumping, driven by gravity's pull and governed by the laws of motion. This process isn't limited to small regions of space. It's happening on every scale. Giant clusters of galaxies spin around each other. Individual galaxies rotate like pinwheels, and inside those galaxies, stars orbit their centers in elegant spirals. Every level of the universe mirrors the same pattern: matter clumping together, gravity pulling inward, and rotation increasing as it condenses. This fractal pattern of spin repeats from the grandest galactic superclusters to the smallest star-forming nebulae. To put it another way, spin is not just a byproduct of cosmic clumping. It's an inevitable consequence of it. Once matter begins to collapse under gravity, any slight imbalance in motion gets amplified. Gravity doesn't just pull, it organizes. And through this organization, it creates motion, order, and structure. Without spin, collapsing clouds of gas might simply fall straight inward, forming featureless blobs. But because they rotate, they develop disks, rings, and cores, shapes that give rise to the planets, moons, and stars we see today. The same principle can be seen in everyday life. When water drains from a sink, it begins to swirl into a vortex as it moves toward the drain. The flow of water becomes organized around a central axis because even the smallest asymmetry gets magnified as it collapses inward. The universe operates in much the same way. Cosmic matter, drawn inward by gravity, naturally organizes into spinning, rotating forms. It's a dance choreographed by the laws of physics themselves. As cosmic clumping continued, the universe entered its next great phase, the birth of stars. Within these spinning clouds, gravity compressed matter until pressure and temperature soared. Deep in the heart of these clouds, atoms began to fuse, igniting nuclear reactions that gave birth to the first stars. Around them, the leftover gas and dust flattened into swirling disks, setting the stage for planets to form. Every star, every planet, every moon owes its spin to that early process of gravitational collapse and rotation amplification. So, from the smallest swirl in a newborn nebula to the majestic rotation of galaxies, the same principle echoes across the cosmos. Gravity pulls, angular momentum resists, and the universe spins faster as it tightens. It's an elegant and self-sustaining cycle. Motion feeding structure, structure feeding motion. The cosmic clumping that began billions of years ago didn't just shape where matter went. It dictated how it moved, ensuring that the universe would never stand still again. Every rotation we see today, the Earth's 24-hour spin, Jupiter's rapid rotation, the swirling arms of the Milky Way, all trace back to those ancient clouds that spun faster and faster as they collapsed. It's a cosmic domino effect, a cascade of motion that began in the earliest epochs and continues to this day. In a very real sense, every sunrise, every orbit, every turning storm is a living echo of that original gravitational choreography. Through cosmic clumping, gravity transformed chaos into rhythm. It took random motion and turned it into the orderly spinning systems that fill our skies. The universe didn't just fall together, it spiraled together, creating the beautiful, rotating structures that define it. Every spin, from a whirling galaxy to the rotation of your own planet beneath your feet, is a continuation of that same ancient process. As the universe continued to take shape and gravity pulled matter into clumps, there was one law quietly ensuring that all this cosmic motion didn't just vanish or fade away. The law of conservation of angular momentum. It's one of the most elegant and unbreakable rules in all of physics, and it's the reason why everything that starts spinning keeps spinning unless something interferes. This single law, simple in principle but vast in consequence, is what ensures that the rotation seeded in the early universe never disappears. It just changes form, moving from one structure to another, from gas clouds to stars, from stars to planets, and onward through every level of cosmic architecture. At its core, the conservation of angular momentum says that if no external torque or twisting force acts on a spinning system, the total amount of its angular momentum remains constant. In everyday terms, it means that once something starts spinning, it will keep spinning at the same rate, or adjust its speed in a predictable way when its shape or size changes, but the overall amount of spin energy stays the same. The universe, in this sense, behaves like a perfect accountant. It never loses or gains angular momentum without cause. We can see this law play out clearly in the human world. Picture a figure skater gliding gracefully across the ice. When she extends her arms wide, she spins slowly. But the moment she pulls her arms in close to her body, her rotation speeds up dramatically. She hasn't received any new push, no extra energy from outside. She simply changed the distribution of her mass. Because her angular momentum must remain constant, reducing her radius forces her rotation rate to increase. The spin speeds up to balance the equation. Now, scale that up to the size of the universe. Those vast clouds of gas and dust collapsing under gravity, the ones that formed stars and planets, follow exactly the same rule. When a cloud of matter begins to contract, its size decreases dramatically, while its mass remains roughly the same. The conservation of angular momentum demands that as the radius shrinks, the rotational speed must increase to compensate. The result? The collapsing cloud begins to spin faster and faster, forming a rapidly rotating disk around a dense central core. That core becomes a newborn star, and the surrounding spinning disk becomes the cradle of planets, moons, and asteroids. This is why every system in the universe, whether it's an atom, a planet, or a galaxy, shows some form of spin. It's an unavoidable consequence of physics. Even the faintest hint of rotation in those early gas clouds, once amplified through collapse, can lead to immense angular velocities. For example, a star-forming nebula might begin with a rotation so slow it takes 1 million years to make a single turn. But as it collapses into a star just a few million kilometers wide, the conservation of angular momentum forces its spin to increase until it completes a rotation in mere days or even hours. The math behind it is straightforward, but the outcome is breathtaking. The same invisible law that governs an ice skater's twirl governs the birth of suns. What's truly fascinating is how universal this law is. It doesn't matter what the object is or what scale it exists on. Whether it's the swirling water in a draining bathtub, a planet orbiting a star, or a galaxy spinning through intergalactic space, the conservation of angular momentum ensures that motion endures. The universe, once set into motion, refuses to stop turning. And that persistence of rotation isn't just mechanical, it's fundamental. It's a cosmic echo of the energy that was unleashed in the Big Bang itself, carried forward through every structure that has ever formed. In this cosmic dance, angular momentum is both the music and the rhythm. It dictates how systems evolve and how they interact. For example, when two celestial bodies collide or merge, like galaxies swirling into each other, their angular momentum doesn't disappear. Instead, it combines, redistributes, and transforms. The merged system may spin slower or faster, or it may tilt in a new direction, but the total angular momentum remains constant. Even the chaos of collisions follows the same ancient rule. When astronomers observe young stars surrounded by spinning disks of dust and gas, they're witnessing conservation of angular momentum at work. Those disks flatten and spin because as material falls inward, it must conserve its rotation. That spinning motion not only shapes the star, but also governs how planets form within the disk. The material doesn't simply fall straight into the star. It spirals inward, creating a kind of cosmic whirlpool where planets eventually coalesce. Without the conservation of angular momentum, that process wouldn't happen, and the universe as we know it, filled with structured, rotating systems, would look utterly different. You can think of it this way. Angular momentum is the guardian of motion. It ensures that nothing in the universe simply starts or stops spinning on a whim. It's the reason Earth still turns after billions of years, the reason our moon continues to orbit, and the reason galaxies can keep their graceful rotation for eons. Even the tiniest electron carries angular momentum that cannot vanish. This constancy connects the smallest particles to the grandest cosmic forms. It's the thread that ties together the quantum and the cosmic. As those vast clouds of gas and dust continued to collapse under gravity, something remarkable began to take shape within their centers, the birth of stars. These immense clouds, known as nebulae, are the cosmic nurseries where stars are born. They may stretch across dozens of light years, their forms delicate and ghostly, yet inside them, physics is at work with relentless precision. The law of conservation of angular momentum, which kept those clouds spinning faster as they contracted, now becomes the architect of starlight itself. Every flicker, every beam of light shining from a star can trace its origins back to that spinning motion deep within the womb of a collapsing nebula. It begins quietly. A section of a giant molecular cloud, often triggered by a nearby supernova explosion or by collisions between clouds, starts to collapse inward under its own gravity. As it does, its rotation, however small, begins to dominate its behavior. The inward pull of gravity competes with the outward centrifugal force created by the spin, shaping the collapsing cloud into a flattened, rotating disk rather than a perfect sphere. This disk is where the magic happens. At the center, matter piles up, density rises, and the temperature climbs to millions of degrees. When the heat and pressure become high enough, hydrogen atoms begin to fuse into helium, releasing vast amounts of energy. At that precise moment, a star is born. But the newborn star doesn't emerge motionless. It inherits the spin of its parent cloud. The angular momentum that once belonged to a gas cloud spanning trillions of kilometers is now concentrated in a sphere barely 1,000,000 kilometers wide. The result is astonishing. Newly formed stars can rotate hundreds of times faster than their parent clouds ever did. Just as an ice skater speeds up when pulling in her arms, the collapsing cloud's spin is magnified as it condenses. The forming star, now a dense ball of plasma, spins rapidly, often completing a rotation in just a few days. Around that spinning star remains a flattened disk of leftover gas and dust, the protoplanetary disk. This disk spins in the same direction as the star because it's made from the same rotating material. The inner regions of the disk orbit faster than the outer parts, creating friction, heating, and a swirling, turbulent environment where tiny grains of dust begin to stick together. Over time, these grains grow into pebbles, rocks, and eventually planets. So, not only is a star born spinning, the entire planetary system around it inherits that same motion. The direction in which Earth rotates and the path it takes around the Sun are direct consequences of the angular momentum of a long-vanished cloud of cosmic dust. This inheritance of spin is why most planets in a solar system tend to orbit in the same direction as their parent star's rotation, and why their paths generally lie in the same plane. The entire solar system, from the smallest asteroid to the Sun itself, is a single spinning remnant of that ancient collapsing cloud. The story of stellar birth is, in truth, a story of preserved motion, a delicate balance between gravity pulling inward and angular momentum spreading outward, keeping the system stable and dynamic at once. In some cases, stars form in binary or multiple systems, where two or more stars orbit a shared center of mass. Here, the distribution of angular momentum becomes even more intricate. Instead of one object taking on all the spin, the momentum is shared between the star's rotation and their orbital dance around one another. This too is a manifestation of conservation at work. The universe never wastes motion. It simply redistributes it in new and balanced ways. The spin of a star isn't static either. Over millions or billions of years, a star's rotation can slow down as it emits stellar winds, streams of charged particles that carry away angular momentum. Magnetic fields play a role too, acting as cosmic brakes that gradually reduce a star's spin rate. The Sun, for instance, rotated much faster in its youth, but over 4.6 billion years, it has slowed considerably. Still, the underlying motion never disappears entirely. Even as stars evolve, die, and explode, they pass that rotational energy forward to the next generation of stars, to remnants like neutron stars, and to the planets that may one day orbit them. It's a beautiful continuity. From a diffuse, cold gas cloud to a burning sphere of plasma, motion is preserved and transformed, but never destroyed. When we observe young stellar systems through telescopes, those brilliant points of light surrounded by shimmering disks of dust, we are witnessing the mechanics of creation, powered by the universe's most fundamental laws. The spin that began as a gentle swirl in a collapsing cloud becomes the defining characteristic of a star's birth and the foundation for everything that forms around it. The formation of spinning stars is not just a mechanical process. It's the universe's way of passing on its original energy, its ancient momentum born from the Big Bang itself. Every star that ignites is a continuation of that story, carrying within its rotation the memory of the cosmos's first movements. And from those spinning stars come the worlds that orbit them, each one inheriting the same rhythm, the same cosmic motion that began billions of years ago when the universe first decided that it would never stand still. Once a star is born, surrounded by that glowing, swirling disk of gas and dust, the stage is set for the creation of planets, and just like their parent star, those planets will inherit the spin and motion of the system they form within. It's one of the most seamless transitions in all of cosmic evolution. The same laws of motion and angular momentum that shaped the birth of a star continue to govern the formation of the worlds that orbit it. In this way, every planet, every moon, every asteroid is a direct descendant of that first rotating cloud of matter. Inside a young star's protoplanetary disk, the material is in constant motion, orbiting the star much like water swirling around a drain. The innermost parts of the disk move the fastest, while the outer regions move more slowly, creating a complex but ordered rotation pattern. Over time, tiny dust particles, microscopic grains of rock and ice, begin to collide and stick together, forming larger clumps called planetesimals. These are the first building blocks of planets, and they too are spinning as they form, rotating in harmony with the larger disk that surrounds them. As these planetesimals grow through countless collisions and mergers, their gravity begins to shape them into roughly spherical bodies. They continue to orbit in the same direction as the disk's overall spin, which itself mirrors the spin of the star. This is why, in most solar systems, all the planets orbit in the same direction and roughly within the same flat plane. The entire system moves like a vast cosmic record, each planet a groove etched in the same circular motion around its central star. On a smaller scale, the same law applies to each planet's own rotation. As they form, planets inherit angular momentum from the swirling material that accretes onto them. The direction and speed of their spin depend on how that material falls in. Sometimes it's smooth and consistent, leading to stable rotation, and other times it's chaotic, producing tilted axes or unusual spin speeds. But even with these variations, the overall trend remains clear. Planets spin and orbit in the same general direction as the disk they were born from, preserving the ancient momentum that began long before they existed. Our own solar system is a perfect example. The Sun spins on its axis, and nearly all the planets orbit it in the same direction, counterclockwise when viewed from above the Sun's north pole. Most planets, including Earth, also rotate in that same direction. This isn't a coincidence. It's the natural outcome of formation from a single, spinning protoplanetary disk. The planets, the Sun, and even many of their moons are all synchronized parts of one enormous rotating system that has been turning together for over 4.5 billion years. As planets grow larger, their spin can also be influenced by the collisions they experience during formation. In the early solar system, space was a violent place. Giant impacts were common, massive collisions between planet-sized bodies that could alter a planet's rotation dramatically. For example, scientists believe that Earth's tilted axis and the formation of the Moon both resulted from a colossal collision between the young Earth and a Mars-sized object called Theia. The debris from that impact eventually coalesced into our Moon, which now helps stabilize Earth's rotation. Even though this was an incredibly chaotic event, it didn't destroy the system's angular momentum. It merely redistributed it, giving rise to new forms of motion. Jupiter, the largest planet in our solar system, tells another version of this story. Its immense spin, completing a full rotation in less than 10 hours, is a consequence of the massive amount of material it accreted from the disk. The more material it gathered, the faster it spun, just as the collapsing gas cloud spun faster as it condensed into a star. The same principle connects the smallest pebble orbiting in a dusty disk to the largest gas giant dominating its system. Even moons follow this cosmic pattern. Most moons orbit their planets in the same direction that their planets orbit their star, and many also rotate in synchronization with their orbit, a state known as tidal locking. Earth's moon is tidally locked, meaning it always shows the same face to us. This locking is a byproduct of gravitational interaction, another expression of the universe's tendency to balance forces while preserving angular momentum. All of this shows that planet formation is not random. It's an orderly process guided by the universe's fundamental rules. Angular momentum provides the blueprint, gravity provides the construction, and time provides the patience. From dust grains to gas giants, every body inherits its motion from the one before it. The spin of a planet is not new motion, it's ancient motion, passed down through cosmic generations. When we look at our solar system today, with its neatly aligned planets circling the Sun in smooth, predictable orbits, we are seeing the fossilized remains of that first great spin. The Earth's daily rotation, the Moon's monthly orbit, and even the tilt that gives us our seasons, all are echoes of a primordial twirl that began billions of years ago when a cloud of gas and dust, light years across, began to collapse and spin. That same rotation now drives the rhythm of our days and nights, the flow of our tides, and the balance of our world. It's humbling to realize that the simple act of the Earth turning beneath our feet each day is a continuation of the universe's earliest motion, a rhythm that began in the cosmic dawn and has never stopped. The planets did not invent their spin, they inherited it, and in doing so, they became part of a cosmic lineage of motion, stretching all the way back to the birth of time itself. While most planets and celestial bodies follow the grand cosmic rhythm, spinning and orbiting in the same general direction as the disks from which they formed, nature, as always, loves exceptions. The universe is not a clockwork machine of perfect symmetry. It's a dynamic, sometimes chaotic interplay of forces, collisions, and gravitational encounters that can twist, tilt, or even reverse the spins of worlds. These exceptions are not errors in the laws of physics. They are expressions of them, reminders that motion in the universe is both orderly and wild, stable and unpredictable. In the early days of a planetary system, things were anything but calm. The protoplanetary disk around a newborn star was a crowded, turbulent place filled with swirling debris, massive rocks, and protoplanets constantly colliding and merging. Each impact carried its own angular momentum, which could dramatically alter the spin or orientation of the growing worlds. This chaotic ballet explains why not all planets spin the same way, or at the same speed. Even though the overall direction of spin and orbit tends to follow the rotation of the original disk, the details of each planet's rotation are often written by violence and chance. Take Uranus, for example, one of the most curious oddities in our solar system. Unlike any other planet, Uranus doesn't spin upright like Earth or slightly tilted like Mars. Instead, it rolls along its orbit almost completely on its side, tilted about 98 degrees from vertical. For centuries, astronomers puzzled over this bizarre orientation. The most widely accepted theory is that long ago, Uranus suffered a catastrophic collision with a massive object, perhaps another protoplanet, roughly the size of Earth. The impact was so powerful that it knocked Uranus onto its side, forever changing the way it spins. This sideways rotation also causes its seasons to be extreme. For decades at a time, one pole basks in continuous sunlight, while the other lies in perpetual darkness. Another example is Venus, a world that seems to defy the general rule entirely. While most planets in our solar system rotate counterclockwise, if viewed from above the Sun's north pole, Venus rotates backward, a phenomenon called retrograde rotation. It spins in the opposite direction of its orbit, meaning that on Venus, the Sun rises in the west and sets in the east. What could cause such a strange reversal? Scientists believe that Venus's slow and backward spin may be the result of massive collisions during its early formation, combined with strong atmospheric tides created by the Sun's gravitational pull on its thick, dense atmosphere. Over time, these tidal forces could have gradually slowed and even reversed its rotation. Venus takes about 243 Earth days to complete one rotation, longer than it takes to complete an orbit around the Sun. It's a world where the cosmic dance seems to have stumbled and then found its own peculiar rhythm. Even Mercury, the smallest planet, doesn't spin the way we might expect. Its rotation is locked in a peculiar resonance with its orbit. It rotates 3 times for every 2 orbits around the Sun. This unusual pattern likely results from the Sun's powerful gravitational influence, which gradually synchronized Mercury's spin and orbit through tidal interactions. These interactions can act like cosmic brakes, slowing a planet's rotation until it becomes locked in a stable pattern. A process that also explains why our Moon always shows the same face to Earth. Beyond our solar system, exoplanets, planets orbiting other stars, show an even more diverse range of spins and tilts. Some spin so rapidly that a day lasts only a few hours, while others are tidally locked, with one side eternally facing their star in scorching heat, while the other side remains in perpetual darkness. Some exoplanets are on highly tilted or even backward orbits relative to their star's rotation. These oddities are likely the result of gravitational encounters with other massive planets or nearby stars, reshaping their paths and spins in complex ways. Even stars themselves can experience shifts in rotation. As stars age, magnetic interactions with their stellar winds can gradually slow their spin. In binary systems, where two stars orbit each other, tidal forces can cause one star's spin to synchronize with its orbital period, just as the Moon is locked to Earth. On even larger scales, entire galaxies can experience changes in rotation direction when they collide and merge, creating new patterns of motion as angular momentum is redistributed among billions of stars. These exceptions, Uranus's sideways tilt, Venus's backward spin, Mercury's slow resonance, are not random quirks, but rather the fingerprints of the universe's dynamic history. Each one tells a story of interaction, of cosmic encounters where energy and motion were exchanged, reshaped, and balanced. The conservation of angular momentum still applies perfectly. It's just that the direction and distribution of that momentum can change through powerful events like collisions, gravitational tugs, and close encounters. The universe doesn't break its own laws, it expresses them in infinite variation. In fact, these oddballs make our understanding of cosmic spin richer, not weaker. They reveal that the same fundamental principles, the interplay of gravity, rotation, and momentum, can produce a vast diversity of outcomes depending on circumstances. Some systems remain neat and orderly, others are tilted, reversed, or chaotic. Yet all of them obey the same invisible rhythm that has guided the cosmos since the Big Bang. So while most worlds follow the flow, spinning in harmony with their parent stars, a few dance to their own tune. They remind us that the universe, though governed by precise laws, is far from predictable. It's a place where structure and chaos coexist beautifully, and where even the exceptions still belong to the same grand symphony of motion. In the cosmic dance, no step is truly wrong. It's all part of the choreography of creation. When we zoom out beyond planets and stars, past the scale of solar systems and nebulae, we find ourselves staring at one of the grandest and most breathtaking phenomena in the universe: galaxies, vast, island-like structures of billions of stars, gas clouds, dust, and dark matter, all bound together by gravity and all, astonishingly, spinning. These cosmic cities of light are not static. They are in constant, graceful motion, rotating around their centers like colossal pinwheels suspended in the dark sea of space. The same law that governs a spinning top on Earth, the conservation of angular momentum, also governs these vast stellar systems, ensuring that galaxies keep turning across billions of years. Our own home, the Milky Way, is a perfect example. Stretching about 100,000 light-years across and containing over 100 billion stars, it rotates once every 225 to 250 million years. That means the last time our solar system was in its current position relative to the galactic center, the dinosaurs were just beginning to walk the Earth. Every star, including our Sun, follows a unique orbit around the Milky Way's heart, moving at tremendous speeds, on average about 220 kilometers per second. Yet despite this blistering motion, the galaxy remains stable, its spiral arms elegantly curving outward in a timeless swirl. But how did galaxies begin spinning in the first place? Just as with stars and planets, their rotation originates from the same process of cosmic clumping and conservation of angular momentum that began shortly after the Big Bang. In the early universe, matter was not evenly distributed. It was slightly lumpy, with regions of higher density where gravity pulled gas, dust, and dark matter together into giant proto-galactic clouds. These early formations weren't perfectly symmetrical. They had tiny irregularities in motion, perhaps small rotational currents caused by gravitational interactions with neighboring matter. As each cloud collapsed under gravity, those faint motions were amplified, and the cloud began to rotate faster, just as a collapsing gas cloud spins up when forming a star. Over billions of years, these massive rotating structures evolved into the galaxies we see today. In spiral galaxies like our own, this rotation is vividly visible. The dense, bright central bulge, home to a supermassive black hole, acts as the core, while vast spiral arms extend outward, filled with stars, nebulae, and planetary systems. The entire structure rotates coherently, though not as a solid body. Instead, each part moves at a different speed. Stars closer to the center complete an orbit faster than those farther out. This phenomenon, known as differential rotation, is crucial to maintaining the spiral shape. Over time, the pattern of the spiral arms is reinforced by waves of star formation triggered by density variations as gas moves through the galaxy's disk. This coordinated motion is an echo of that same cosmic law. Angular momentum preserved and distributed across unimaginable scales. Even though individual stars are separated by vast distances, they all contribute to the galaxy's overall rotation. Every orbit, every swirl of interstellar gas, adds its share of motion to the collective spin. The galaxy, in a sense, is a single organism, a self-sustaining, rotating system in which each part participates in a grand, unified movement. And galaxies don't just rotate in isolation. They move through space, interact, and even collide with each other, all while conserving angular momentum. When two galaxies approach one another, their immense gravitational fields pull and twist, distorting their shapes and flinging stars outward in tidal streams. Yet even in this chaos, the total angular momentum of the system remains constant. The merging galaxies eventually settle into a new equilibrium, often transforming from two distinct spirals into a single, more spherical, elliptical galaxy. The direction and speed of the final galaxy's spin depend on how the angular momentum from both progenitors combines. It's cosmic alchemy, with motion as the element that never disappears, only changes form. We can see this process unfolding across the cosmos. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have captured breathtaking images of galaxies in various stages of collision and merger, each one a ballet of gravity and spin. In these cosmic encounters, stars rarely collide directly because of the vast distances between them. Instead, their orbits are reshaped, and gas clouds within the galaxies interact violently, triggering bursts of star formation. Through it all, the overall angular momentum of the system dictates how the galaxies evolve, ensuring that rotation remains a defining feature even after the most cataclysmic transformations. Interestingly, not all galaxies look or behave the same way. Elliptical galaxies, for example, appear more like glowing, featureless balls of stars rather than elegant spirals. Their rotation is often slower and more chaotic, with stars moving in random directions rather than along orderly, circular paths. This difference likely arises from their violent pasts. Many ellipticals are the remnants of spiral galaxy mergers, their original spins disrupted and redistributed by those colossal collisions. Still, even here, angular momentum has not vanished. It's simply been rearranged among countless individual stellar motions. On even larger scales, galaxies themselves are part of rotating systems. Clusters of galaxies, massive cosmic neighborhoods bound together by gravity, can also have overall rotational motion, shaped by the angular momentum they inherited from the primordial clouds that formed them. This nested hierarchy of spin, stars within galaxies, galaxies within clusters, clusters within superclusters, suggests that rotation is not just a local phenomenon, but a fundamental feature of the universe at every scale. What's astonishing is the coherence of it all. The same principle that governs the spin of an electron or a planet also governs the motion of galaxies millions of light years across. The laws of angular momentum operate seamlessly across this entire spectrum of existence, linking the smallest particles to the largest cosmic structures. The universe doesn't differentiate between the micro and the macro. It follows the same rhythm, the same rules, everywhere. When we gaze through a telescope and see those magnificent spiral galaxies turning slowly in the darkness, we are witnessing the living history of cosmic motion. Each rotation is the continuation of a process that began in the earliest moments of time, when the first uneven clumps of matter began to collapse and spin. Every glowing arm, every orbiting star, every drifting nebula is part of that great, ancient movement, the universe conserving its motion, balancing its forces, and expressing its eternal dance through the turning of galaxies. So, when you look up at the Milky Way stretched across the night sky, remember, it's not standing still, it's rotating, carrying us with it in a vast cosmic whirl that began billions of years ago and will continue long after we're gone. The same law that keeps a planet spinning on its axis keeps entire galaxies in motion. From the smallest atom to the grandest cluster of galaxies, the universe's story is one of perpetual rotation, a story written in every turn of the stars. As we marvel at the elegant spinning majesty of galaxies, there's a profound mystery hidden within their motion, something that defies our expectations and even the very equations that describe how gravity should work. When astronomers first began measuring the rotation speeds of galaxies in the mid-20th century, they noticed something astonishing. The stars at the edges of galaxies were moving far faster than they should be if the only mass present was the visible matter, stars, gas, and dust. According to Newtonian physics, and even Einstein's general relativity, the farther a star is from a galaxy's center, the slower it should orbit, much like how the outer planets in our solar system move more slowly than the inner ones. But that isn't what the data showed. Instead, galaxies seemed to rotate as if they were much heavier than they appeared, their outer edges spinning almost as fast as their cores. This observation presented an enormous puzzle. Something unseen had to be providing additional gravity to hold these rapidly spinning galaxies together. Otherwise, the outer stars should have been flung into intergalactic space long ago. The visible mass simply wasn't enough to explain the observed rotation curves. The only explanation that fit was that galaxies are filled with and surrounded by an enormous amount of invisible matter that exerts gravitational force but doesn't emit or absorb light. Scientists called this mysterious substance dark matter. Dark matter doesn't interact with electromagnetic radiation, meaning we can't see it, touch it, or detect it directly using conventional instruments. Yet its presence can be inferred through its gravitational effects. It acts as a kind of cosmic glue, binding galaxies together and shaping their rotations. Without it, the elegant spirals we see through telescopes might never have formed, or, if they did, they would have quickly unraveled. Dark matter provides the hidden mass that allows galaxies to spin as fast as they do without flying apart. Dark matter forms massive halos around galaxies, vast spherical regions of invisible mass that extend well beyond the visible stars. The gravitational pull from these halos provides the extra force needed to keep the outer stars moving at the speeds we observe. In our own Milky Way, dark matter is thought to make up the vast majority of its total mass. Astronomers estimate that for every bit of ordinary matter we can see, like stars, planets, and gas, there's about 5 times as much dark matter holding it all together. This invisible scaffolding doesn't just stabilize galaxies, it played a critical role in their very formation. In the early universe, dark matter clumped together first, forming massive gravitational wells that attracted ordinary matter. Those dense regions became the seeds of the first galaxies, setting them spinning as they collapsed under their combined gravitational pull. The presence of dark matter also explains why galaxies within clusters move the way they do. In the 1930s, astronomer Fritz Zwicky first noticed that galaxies in the Coma cluster were moving too quickly to be held together by the visible matter alone. He concluded that some missing mass must be providing the extra gravity, a radical idea at the time that would later become central to our understanding of the cosmos. Decades later, Vera Rubin's meticulous measurements of galaxy rotation curves provided the decisive evidence. Galaxies were behaving as if most of their mass was invisible. Her work fundamentally changed astrophysics and solidified the concept of dark matter as a cornerstone of modern cosmology. But dark matter's role goes beyond just explaining galaxy rotation. It shapes the large-scale structure of the universe itself. When cosmologists map the distribution of galaxies, they find that they form a vast web-like network, the cosmic web, with filaments and nodes of dense matter stretching across billions of light-years. Computer simulations show that this structure could only have formed if dark matter were present, guiding the gravitational clustering of galaxies and helping sustain their motion and arrangement. Despite its profound influence, dark matter remains one of the greatest mysteries in science. We know it's there, we can calculate its effects, but we don't yet know what it is. Some theories suggest it's made up of exotic, as yet undiscovered particles that barely interact with ordinary matter, perhaps WIMPs, weakly interacting massive particles. Interacting massive particles or axions. Others propose that our understanding of gravity might need to be modified at cosmic scales. Yet, whatever its true nature, dark matter's gravitational presence is undeniable. It is the silent architect of cosmic motion. So when we look at a spiral galaxy turning in the depths of space, we're not just seeing stars and gas spinning in isolation. We're seeing the visible tip of a vast, invisible structure. The stars are like glowing leaves caught in a whirlpool whose shape and strength are defined by the unseen depths below the surface. Without that hidden mass, the whirl would lose coherence. The dance would fall apart. Dark matter ensures that the universe's great spinning structures, galaxies, clusters, and even the cosmic web can maintain their stability and motion across billions of years. In this sense, dark matter is the unsung hero of the cosmic dance. It doesn't shine, it doesn't sparkle, but its gravitational hand guides every twirl and spin across the universe. It binds the visible to the invisible, ensuring that the rotation begun at the dawn of time continues unbroken. Every orbit, every spiral, every galactic turn owes its existence not just to the matter we can see, but to the vast, shadowy substance that pervades the cosmos, an unseen force that keeps the dance alive. As we continue outward through the hierarchy of cosmic motion, from atoms to planets, from stars to galaxies, we eventually arrive at the most extreme spinners of all, black holes. These are not just ordinary rotating bodies. They are the ultimate embodiment of angular momentum in its most concentrated and violent form. If the spin of a planet or a star is a dance, then the spin of a black hole is a cosmic storm, a twisting of space-time itself so intense that even light cannot escape its grasp. A black hole forms when a massive star runs out of nuclear fuel and collapses under its own gravity. When the inward pull of gravity overcomes all other forces, the star's core collapses into a singularity, a point of infinite density, surrounded by an invisible boundary called the event horizon. This boundary marks the region beyond which nothing, not even light, can escape the black hole's gravitational pull. But here's the extraordinary part. If the original star was spinning, that rotation doesn't just disappear during the collapse, it gets amplified. Because of the conservation of angular momentum, the collapsing core spins faster as it shrinks, just as an ice skater twirls faster when pulling in her arms. But in the case of a star collapsing into a black hole, the scale of that acceleration is beyond comprehension. The radius of the star might shrink from millions of kilometers to just a few kilometers, forcing its rotational speed to increase by staggering amounts. The result is a spinning black hole that can rotate at nearly the speed of light. This spin doesn't merely cause the black hole to rotate as an object would, it actually drags space-time around with it. This phenomenon, predicted by Einstein's general theory of relativity, is known as frame dragging. In the region near a rotating black hole, space and time themselves are twisted and pulled along by the black hole's spin, forming what physicists call the ergosphere, a distorted zone outside the event horizon where nothing can remain still relative to the distant universe. In the ergosphere, even light must move in the direction of the black hole's rotation, swept up by the immense warping of reality. Imagine space-time as a giant, flexible fabric. A non-rotating black hole acts like a deep, motionless pit in that fabric. But when the black hole spins, it doesn't just sit still, it whirls, dragging the fabric into a swirling vortex. Anything that enters that region is forced to spin with it, whether it's gas, dust, or even beams of light. This is the universe's most extreme expression of angular momentum, rotation so powerful that it reshapes the geometry of existence itself. Astronomers categorize these cosmic whirlwinds as Kerr black holes, named after the mathematician Roy Kerr, who first solved the equations describing them in 1963. Kerr's solution revealed that a rotating black hole is far more dynamic and complex than a non-spinning one. Not only does it possess a gravitational pull that warps space-time, but it also has rotational energy that can, under certain conditions, be tapped. Theoretical physicist Roger Penrose proposed that if an object enters the ergosphere and splits in two, one part falling into the black hole and the other escaping, the escaping part can actually gain energy from the black hole's rotation. This process, known as the Penrose process, shows that even the spin of a black hole can, in theory, be harnessed. But perhaps the most visually striking evidence of black hole spin comes from the jets, colossal streams of energy and matter that some black holes emit from their poles. These jets, extending for thousands or even millions of light years, are powered by the immense rotational energy of the black hole and the magnetic fields that surround it. As gas and dust spiral inward toward the event horizon, they form an accretion disk, a blazing, spinning disk of superheated matter that rotates at relativistic speeds. The material in this disk doesn't fall straight in. It spirals around the black hole, following the curve of space-time, heating up through friction and compression until it glows with extraordinary brightness. This process can convert mass into energy with astonishing efficiency. Up to 40% of the infalling material's mass is transformed into radiation, compared to less than 1% in normal nuclear fusion. All of this motion, every swirl of the accretion disk, every twist of the magnetic field, every blast of relativistic jet, is a product of spin. The black hole's rotation dominates the region around it, dictating how matter moves, how energy flows, and even how time behaves. If a black hole spins fast enough, close to the theoretical maximum speed known as an extremal Kerr black hole, It can rotate so quickly that the event horizon and the singularity merge into a single, infinitely thin ring of energy. In such cases, the black hole's spin becomes nearly absolute, a pure expression of angular momentum bound within the limits of physics itself. Even light, the fastest thing in the universe, is affected by this rotation. As photons pass near a spinning black hole, their paths are bent and twisted by the distorted spacetime, creating spectacular visual effects. This is what we see in images of black holes captured by instruments like the Event Horizon Telescope. Rings of light warped into a glowing halo, showing not just the pull of gravity, but the influence of rotation. The bright side of the ring corresponds to light moving in the same direction as the black hole's spin, boosted in brightness by the rotational motion, while the dimmer side corresponds to light moving against it. What's fascinating is that black hole spin isn't just an isolated phenomenon. It connects to the story of cosmic evolution itself. The angular momentum that drives black holes comes from the same source as all other cosmic motion: the initial spin of collapsing matter, amplified through gravitational collapse and preserved by the laws of physics. Some of the fastest spinning black holes ever observed, rotating more than 1,000 times per second, were born from massive, rapidly rotating stars. Others gained their spin through billions of years of consuming surrounding matter and merging with other black holes. In every case, their motion is a testament to the universe's deep commitment to conserving angular momentum. Even in the most extreme conditions imaginable, where matter, energy, and space itself are twisted into near incomprehensible forms, the same principle endures. What begins spinning must continue spinning, its motion reshaped, but never destroyed. Black holes remind us that spin is not just a feature of the universe, it is one of its defining powers. From the gentle rotation of a planet to the violent whirl of a singularity, the same ancient rule applies. In the heart of a black hole, where gravity conquers light and time folds in on itself, the universe still dances. Its steps may be hidden, its rhythm too deep for the eye to see, but the motion endures. The cosmos turns endlessly, even in its darkest places. If we now reverse direction, zooming inward instead of outward, we find that spin isn't only a feature of stars, planets, and galaxies. It lives in the smallest building blocks of existence itself. Deep within every atom, the same mysterious principle reappears in a different guise, woven into the very fabric of quantum reality. Electrons, protons, and neutrons, all the fundamental particles that make up matter, possess what physicists call intrinsic spin. And though it shares the name, this quantum spin is not a simple mechanical rotation like the turning of a planet or a wheel. It's something more abstract, more profound, a fundamental form of angular momentum that exists without any need for physical spinning at all. To understand this, imagine zooming down to the atomic level. A single atom is mostly empty space, a dense nucleus of protons and neutrons at its center, surrounded by a cloud of electrons moving so fast that they seem to form a blur. For a long time, scientists thought of electrons as tiny planets orbiting the nucleus, but quantum mechanics shattered that picture. Electrons don't orbit in neat, predictable paths. They exist as probability waves smeared through space. And yet, each of these tiny quantum entities carries a measurable amount of angular momentum, what we call its spin. When scientists first discovered spin in the early 20th century, they were astonished. The term spin was coined because certain experimental results, like the way electrons respond to magnetic fields, behaved as if the electrons were tiny charged spheres spinning on their own axes. But there was a problem. Electrons are point-like particles. They have no size or structure that could physically spin. Yet the equations describing them showed they still possessed angular momentum and an associated magnetic moment. This meant that spin was not a result of physical rotation, but an intrinsic, built-in property of the particle, something fundamental to its identity, like mass or electric charge. Every elementary particle has a specific spin value measured in units of h-bar over 2, where h-bar is the reduced Planck constant. For electrons, protons, and neutrons, that value is 1/2, which is why they are called fermions. Fermions are the particles that make up matter, and their half-integer spin gives rise to one of the most important rules in quantum mechanics, the Pauli exclusion principle. This principle states that no two fermions can occupy the same quantum state at the same time. It's the reason why electrons stack in different energy levels around an atom, giving rise to the structure of the periodic table, and ultimately to all the chemistry that defines the material universe. In other words, the spin of electrons is directly responsible for why matter has structure, why atoms don't collapse, and why you can touch, see, and breathe the world around you. But there's more. Not all particles have half-integer spin. Some, like photons, the particles of light, have integer spin values, 1, 2, etc. These are called bosons, and they obey a completely different set of rules. Unlike fermions, bosons can share the same quantum state, which allows them to pile together and act in unison. This property of bosons leads to phenomena like lasers, where countless photons move in perfect synchronization, and superfluidity, where atoms flow without friction. So, the concept of spin doesn't just describe motion, it determines the very behavior of matter and energy. What's truly astonishing is how spin, even at this smallest scale, still obeys the law of conservation of angular momentum, the same law that keeps galaxies turning. When two particles interact, the total spin before and after must remain the same. In nuclear reactions, atomic transitions, and even particle collisions, angular momentum is never lost. It's only exchanged or transformed. This means that the cosmic principle of rotation, the one governing everything from planets to galaxies, extends seamlessly into the quantum world. The universe keeps its books balanced down to the last decimal of angular momentum, no matter the scale. Spin also lies at the heart of the mysterious link between matter and magnetism. When electrons move through a material, their spins can align, producing a net magnetic field. This alignment is what gives magnets their power. On a deeper level, quantum spin is responsible for many of the strange and beautiful behaviors in modern physics. Everything from the fine structure of atomic spectra to the operation of quantum computers, which use the spin states of electrons or atomic nuclei as qubits, the building blocks of quantum information. And the more scientists study spin, the stranger it becomes. When measured, a particle's spin behaves in a way that defies classical intuition. It doesn't point in a definite direction until it's observed. In experiments like the Stern-Gerlach experiment, particles are sent through a magnetic field and split into distinct paths depending on their spin orientation, up or down, never anywhere in between. This binary nature of spin reveals its quantum essence. It's not a smooth, continuous motion, but a discrete, quantized property bound by the probabilistic rules of the quantum world. In fact, quantum spin connects deeply to the mathematics of symmetry in physics. According to group theory and the framework of quantum field theory, spin is what determines how particles transform under rotations in spacetime. It's a manifestation of the same rotational symmetry that gives rise to the conservation of angular momentum. In other words, the fact that particles have spin is not random. It's a direct consequence of the universe's fundamental symmetry, the same cosmic order that governs the rotation of galaxies and the orbit of planets. This reveals something profound. Rotation, in all its forms, is not just a behavior of matter. It's a property of reality itself. From the smooth rotation of a planet to the abstract quantum spin of an electron, angular momentum is a thread that runs through the entire tapestry of existence. The universe doesn't just allow spin, it requires it. When you think about it, this continuity between the quantum and cosmic scales is nothing short of poetic. The electrons spinning in your atoms and the galaxy spinning across the night sky are both manifestations of the same principle, expressed through different languages of physics. The motion that sustains the cosmos is the same motion that gives form to your body, your breath, your mind. Spin is the universe's fingerprint, present in everything, from the smallest particle to the grandest cluster of stars. And so, as we zoom back out from the atomic scale, we begin to see that the line between the microscopic and the macroscopic isn't a boundary at all. It's a bridge, a continuous flow of motion that connects the invisible world of quantum particles to the majestic rotations of galaxies. Everywhere we look, the universe turns, and at every scale, from the smallest quantum leap to the vast cosmic swirl, the rhythm of spin never stops. When we step back and view the universe as a whole, something extraordinary becomes clear. From the tiniest quantum particles to the largest cosmic structures, motion is not an accident. It's a fundamental law woven into the fabric of existence itself. The same principle that governs the spin of an electron also dictates the rotation of planets, the orbits of stars, and the majestic spirals of galaxies. On every scale, the universe seems to sing the same song in different octaves, repeating its patterns of rotation and balance like a cosmic symphony of angular momentum. At first glance, the quantum world and the cosmic world seem impossibly far apart. One deals with the infinitesimal, where particles flicker in and out of probability clouds, and the other with the immense, where stars and galaxies move across gulfs of millions of light years. Yet, the deeper science delves into both realms, the more connections we find. Spin, the intrinsic angular momentum of quantum particles, and rotation, the macroscopic turning of celestial bodies, are not separate phenomena. They are two expressions of the same universal truth, that motion is inherent to being. Consider this. An electron doesn't start spinning because something acted upon it. It simply has spin. It's a fundamental property, one that defines its identity just as much as its charge or mass. In the same way, the universe itself didn't begin rotating because of some external influence. From the very instant of the Big Bang, motion was built into its structure. The primordial fluctuations, the unevenness in the distribution of energy, and the laws of physics themselves all ensured that rotation, vibration, and oscillation would exist forever after. This mirroring between the micro and the macro reveals a kind of cosmic self-similarity. Both atoms and galaxies follow rules of balance, governed by angular momentum. When an electron's spin aligns in a certain way, it determines how atoms bond, how energy is emitted or absorbed, and even how light interacts with matter. On the grandest scale, when galaxies rotate, their angular momentum dictates how stars orbit, how matter clumps, and how energy flows through space. Each level of reality preserves and transforms angular momentum, passing it upward and downward through the hierarchy of existence. The connection goes even deeper when we consider how symmetry defines both realms. In quantum physics, the conservation of angular momentum arises from rotational symmetry, the idea that the laws of nature don't change no matter how you rotate your frame of reference. This same principle applies to the cosmos as a whole. The universe doesn't prefer one direction of spin over another. For every galaxy rotating clockwise, another spins counterclockwise, maintaining overall balance. What we see then is not randomness, but a deep, mathematical order that links the smallest particle to the largest structure. Even the forces that govern these scales are united by this principle. Electromagnetism, which depends on the spin and charge of particles, gives rise to magnetism, light, and atomic stability. Gravity, on the other hand, shapes the orbits and spins of planets, stars, and galaxies. Yet both forces are rooted in the same space-time fabric, one that bends, twists, and rotates according to the mass, energy, and motion it contains. Spin, in both senses, is the universe's way of balancing its own dynamics. It's as if the cosmos itself has a built-in rhythm, a perpetual balancing act between inertia and motion, structure and flow. Some physicists and philosophers even suggest that spin is more than a mechanical feature. It might be a signature of the universe's deepest geometry. In modern physics, particularly in theories like quantum field theory and general relativity, spin is not an add-on. It emerges naturally from the way fields behave under rotation. The mathematics that describe an electron's spin are cousins to those that describe the curvature of space-time around a spinning black hole. Both are governed by how nature responds to rotation, both follow conservation laws that preserve motion, and both remind us that reality itself is not static but dynamic by design. If we take a step further, we can see how intimately connected we are to this universal motion. The atoms in your body, spinning, vibrating, exchanging quantum angular momentum, are made of the same material as the stars that orbit in the galactic disk. The very spin that defines the particles in your cells mirrors the spin that drives the Milky Way's rotation. The same mathematical symmetries that make electrons behave predictably also ensure that galaxies maintain their shape and motion. On every level, from quantum fields to celestial spheres, spin is the common language, the heartbeat of the cosmos pulsing through every scale of being. In this light, stillness is an illusion. Even when you sit perfectly motionless, the electrons within you are spinning, the Earth beneath you is turning, the solar system is orbiting the galactic center, and the galaxy itself is revolving through space. You are, quite literally, part of a cosmic motion that never stops. The energy that sustains this movement, the angular momentum that began in the earliest seconds after the Big Bang, continues to flow through everything, from you to the edge of the observable universe. What's even more humbling is how consistent the universe is about this. Across 60 orders of magnitude, from the subatomic to the supergalactic, angular momentum behaves the same way. It's conserved, exchanged, amplified, but never destroyed. That universality hints at a profound truth. The laws of physics aren't just descriptions of how things move. They are expressions of an underlying unity that connects all motion, all spin, all rotation into one continuous cosmic process. In the spinning of an electron, we see the potential for chemistry, for matter, for life. In the spinning of galaxies, we see the architecture of the cosmos, the clustering of stars, and the flow of time. Both are manifestations of the same cosmic pattern, scaled differently, but singing the same fundamental melody. The micro reflects the macro, and the macro reflects the micro. The universe, it seems, is a fractal of motion, every level echoing the next. When we realize this, the question, "Why does everything spin?" transforms into something deeper. It's not merely a matter of mechanics, it's a reflection of the universe's essence. Spin is not a side effect of existence, it is existence in motion. Without it, there would be no structure, no stability, no energy, no life. From the quantum heartbeat of particles to the majestic pirouette of galaxies, the cosmos declares through every turn and twirl that motion is the natural state of reality. The connection between atomic spin and cosmic rotation reveals something profoundly simple yet infinitely beautiful. The universe is not a static sculpture, it is a living dance. Every atom, every star, every galaxy, and every thought is part of that dance, bound together by the same eternal rhythm of motion. The universe spins because it must, because that's what it means to be. And in that endless turning, it writes the story of everything. If everything in the universe, from the tiniest particle to the grandest galaxy, is spinning, then it's only natural to ask, why not stillness? Why isn't the universe perfectly calm, frozen in a motionless state of equilibrium? Why is there movement at all? Why do stars whirl, planets orbit, atoms vibrate, and particles flicker endlessly? It's a question that strikes at the heart of existence itself, because to understand why there is motion is to understand why there is a universe at all. The simple, astonishing truth is that complete stillness is impossible once energy exists. In fact, motion and energy are inseparable. The very birth of the universe, the Big Bang, ensured that the cosmos would never be still again. When that first explosion of space and time occurred, it filled the universe with energy, matter, and momentum. That initial burst set everything in motion, and because of the conservation laws that govern physics, especially the conservation of energy and angular momentum, this motion could never simply fade away. The universe has been moving ever since, endlessly redistributing the same primordial energy through space and time. To imagine a perfectly still universe, we have to imagine a universe with no energy, no matter, and no time, because motion is a fundamental consequence of all three. Energy manifests as vibration, oscillation, rotation, and movement. Matter cannot exist without the constant jostling of its particles. And time itself is defined by change, by one state giving way to another. If nothing moves, nothing changes. Without motion, there would be no time. A perfectly still universe would be not just empty, it would be non-existent. Even the smallest components of reality refuse to rest. Electrons orbit their atomic nuclei not as particles traveling fixed paths, but as dynamic waves of probability. Quantum mechanics tells us that particles can never have exactly zero energy. There is always a faint, irreducible hum of activity known as zero-point energy. This means that even in the coldest, emptiest reaches of space, even in what we call a vacuum, there is movement. Tiny fluctuations in energy cause particles to appear and disappear in pairs, borrowing energy from the quantum field in a ceaseless, microscopic dance. The vacuum, far from being truly nothing, is a restless sea of virtual motion. And so, the universe doesn't need an external cause to move. It moves because that's what energy does. Motion is energy's natural expression, and energy is the universe's most fundamental ingredient. In this way, the cosmos is like an eternal pendulum, swinging because it cannot do otherwise. The momentum given to it at the moment of creation is conserved everywhere, in every atom, in every star, in every rotation of every galaxy. This principle extends upward through every scale. The Earth spins because it formed from a rotating cloud of dust that could not stop spinning. The Sun turns because the angular momentum of the collapsing gas that created it could not vanish. The Milky Way rotates because the mass that formed it inherited spin from the earliest gravitational clumps in the primordial universe. Each level inherits motion from the one before it, tracing back to that first, energetic moment when space itself began expanding. The universe is, quite literally, an echo of that first motion. Now imagine, for a moment, what it would mean for the universe to be truly still, for every particle to cease movement, for every vibration to stop, every star to freeze, every atom to rest. That would mean no heat, no sound, no gravity, no light, and no life. Temperature is just the measurement of motion on the atomic scale. the jiggling of molecules and atoms. Without motion, temperature would drop to absolute zero, and even quantum fluctuations would vanish. But according to our best understanding of physics, absolute zero cannot be reached. Nature forbids it. There will always be some trace of motion, some faint whisper of energy. Stillness, then, isn't natural, it's impossible. Even when things seem stationary to us, they're moving through layers of motion so vast and intertwined that we can't perceive them. You might be sitting perfectly still right now, yet the Earth is spinning beneath you at about 1,670 kilometers per hour. At the same time, the Earth is orbiting the Sun at 107,000 kilometers per hour, while the Sun orbits the Milky Way at about 828,000 kilometers per hour. And even our galaxy is racing through space toward the Virgo cluster at over 1 million kilometers per hour. Stillness, as far as the universe is concerned, is an illusion of perspective. This never-ending motion gives rise to stability through balance. Just as a spinning top remains upright because of its rotation, the universe itself maintains its structure through motion. Spin creates equilibrium. Orbits create order. Without movement, stars would collapse under gravity, planets would fall into their suns, and the delicate cosmic architecture that sustains galaxies would disintegrate. The balance between gravity and motion is what holds everything together. In many ways, motion is not just a property of the universe, it is the condition for its existence. Without motion, there would be no energy, no temperature, no time, no change, no cause and effect. Even the act of thinking, the firing of neurons in your brain, is a form of motion. Electrical impulses and chemical exchanges in constant flux. Life itself is sustained by movement, the circulation of blood, the beating of hearts, the vibrations of molecules in every cell. So when we ask, why isn't the universe at rest? The answer is beautifully simple and profoundly deep. Because rest is impossible in a universe that exists. To exist is to move. To be is to change. From the trembling of subatomic particles to the spin of galaxies, motion is the defining signature of reality. If the universe could speak, perhaps it would say, "I move, therefore I am." The rhythm of motion is the rhythm of being. Stillness belongs not to the cosmos, but to imagination, to a place outside of time and energy, a place that cannot exist within this living, turning, breathing universe. The cosmos does not rest because it is motion, an eternal unfolding of energy, forever balancing, forever dancing, forever alive. But if motion is the heartbeat of the universe, it's not always graceful or orderly. In fact, much of the cosmos's motion, especially its spinning and swirling, is born from chaos. The universe's dance is not a calm waltz. It's a fiery, unpredictable ballet of collisions, mergers, and cosmic upheavals. And yet, even in the most violent events imaginable, planets smashing together, stars tearing each other apart, entire galaxies colliding, the spin never truly stops. It doesn't vanish into nothingness. It merely changes form, flowing from one system to another, creating new motions, new tilts, and new rhythms across the cosmos. From the very beginning, the universe has been a place of collisions. During the early stages of planet formation, young solar systems were chaotic battlefields. Hundreds of growing protoplanets and countless smaller bodies orbited their stars in unstable paths, frequently crashing into one another. These collisions were catastrophic, melting rock, vaporizing metal, and reshaping worlds. Yet, through all of it, the law of conservation of angular momentum remained absolute. When two bodies collided, their spins and orbits combined, merging into a single new pattern of motion. The energy of their impact might have been violent, but the motion persisted, transformed, not destroyed. Take Earth as an example. Our planet's current rotation, its tilt, and even its moon are the products of a colossal collision that occurred around 4.5 billion years ago. A Mars-sized object, now called Theia, struck the young Earth in a glancing blow so powerful that it nearly tore the planet apart. The impact sent molten rock and debris spraying into orbit, which later coalesced into the Moon. That same collision also altered Earth's rotation, giving it the 23.5-degree tilt that produces our seasons. The Earth's spin didn't end in that moment of chaos. It was reborn, reshaped into the rhythm that now defines our days and nights. And Earth's story is far from unique. Throughout our solar system, we see the fingerprints of ancient collisions written in spin. Uranus's bizarre sideways rotation, for example, is almost certainly the result of a massive impact during its formation, knocking it onto its side. Venus, too, likely suffered one or more titanic collisions that reversed its rotation entirely, leaving it spinning backward compared to most other planets. Even smaller bodies, like asteroids and moons, bear the scars of impacts that altered their spins and orbits. Every tilt, wobble, and irregular rotation we see in the solar system is a record of energy exchanged through cosmic encounters. But these collisions don't just affect planets, they shape galaxies themselves. On the grandest scale, galaxies are constantly colliding and merging, driven together by gravity over billions of years. When two spiral galaxies meet, their graceful arms twist and tangle, their stars flung into vast tidal streams that stretch for hundreds of thousands of light years. For a time, it looks like chaos, a ballet of destruction. But even here, spin endures. The galaxy's angular momenta combine, redistributing their rotational energy into new patterns. Sometimes the result is a new elliptical galaxy, rounder and slower spinning than its spiral parents. Other times, the merger sparks waves of new star formation, giving birth to brilliant clusters that spin on their own. Astronomers have captured incredible images of these galactic collisions in action. When two galaxies merge, the gravitational forces between them don't annihilate motion, they transform it. Stars rarely collide directly. Space is vast after all, but their orbits are reshaped. Gas clouds compress and swirl, igniting bursts of starbirth. The supermassive black holes at each galaxy's center spiral inward, eventually merging in a titanic event that releases more energy than all the stars in either galaxy combined. And through it all, the universe's accounting remains perfect. Angular momentum conserved, motion preserved, spin reborn in new and astonishing forms. This cycle of chaos and creation reveals one of the universe's deepest truths. Disorder does not destroy order, it feeds it. Collisions, though violent, are part of the cosmic process of renewal. They redistribute spin, reorient axes, and set new bodies and systems in motion. The same law that governs the calm rotation of a planet also governs the chaos of a galactic merger. The difference is only in scale and perspective. Even in smaller, quieter systems, this principle holds. Binary stars tug on each other, transferring angular momentum back and forth as they orbit. Moons pull on their planets, gradually slowing their rotation through tidal forces while moving farther away. These slow dances of exchange can last billions of years, but the rule is always the same. Angular momentum is conserved. When one body loses spin, another gains it. When one orbit shrinks, another expands. The universe moves its motion around like a cosmic currency, always keeping the total balance intact. You could say the cosmos is a master recycler of motion. Nothing is wasted. Every collision, every wobble, every tilt adds to the grand story of spin. The Milky Way itself has grown through countless mergers, absorbing smaller galaxies like the Sagittarius dwarf galaxy, whose remnants are still visible as stellar streams wrapped around our own. Our galaxies spin today. The slow, majestic rotation that carries us through space is partly inherited from the angular momentum of all the galaxies it has ever consumed. We are, in a sense, the product of billions of years of cosmic collisions, each one passing on a little more motion, a little more spin, to the next generation of stars and worlds. So while the universe can appear violent and chaotic, beneath that chaos lies profound order. The same principle that keeps a skater spinning applies even to galaxies tearing each other apart. The collisions that seem destructive are, in truth, creative. They reshape motion into new forms, maintaining the eternal continuity of spin that began at the dawn of time. The universe, then, doesn't resist chaos. It uses it. It turns destruction into structure, collision into creation, and disorder into dance. Every tilt of a planet, every ring of debris, every spiral arm in a galaxy is a testament to that eternal transformation of motion. Spin is not fragile, it's indestructible. Even when worlds collide, the dance continues, new rhythms born from old ones, forever weaving motion through the cosmos. Despite all the chaos, collisions, and constant motion that define the cosmos, the universe somehow manages to sustain remarkable stability. The same spinning that began billions of years ago, born from the Big Bang's first unevenness and shaped by gravity's relentless pull, is not just a force of motion, but one of balance. Spin creates stability. It's what keeps planets from collapsing, stars from wobbling apart, and galaxies from disintegrating. Without rotation, the very structures that make up the universe would lose their shape, their harmony, and their endurance. When an object spins, it generates a property known as centrifugal force, which acts outward from the axis of rotation. This outward push doesn't cancel gravity, but it balances it in subtle and essential ways. On Earth, for example, the planet's rotation causes it to bulge slightly at the equator and flatten at the poles. Earth is not a perfect sphere. It's an oblate spheroid, because the centrifugal force from its spin counteracts gravity's inward pull just enough to create this shape. This balance gives Earth a stable, predictable rotation, and it helps regulate everything from our day-night cycle to the distribution of atmospheric pressure that drives weather patterns. The same principle applies to other planets and stars. Jupiter, the fastest spinning planet in our solar system, completes one rotation every 10 hours despite its enormous size. Because of that rapid spin, Jupiter's equatorial diameter is more than 9,000 kilometers greater than its polar diameter, a massive difference caused entirely by centrifugal force. And yet, that very flattening contributes to Jupiter's stability. Its spin creates a steady balance of forces that keeps the planet's enormous mass evenly distributed, helping maintain its shape and preventing gravitational collapse under its own weight. Stars, too, depend on spin for their structure and equilibrium. When a star forms from a collapsing cloud of gas and dust, its rotation helps it find balance between gravity and pressure. Without any spin, gravity would pull inward uniformly, and the star would collapse far more rapidly, possibly becoming unstable or even failing to ignite. But rotation introduces a stabilizing element. The centrifugal force slightly counteracts gravity, spreading mass and energy more evenly across the star's volume. This balance helps regulate how the star burns its fuel, influencing its lifespan and behavior. In some cases, spin can actually prevent total collapse. Consider neutron stars, the incredibly dense remnants left behind after massive stars explode in supernovae. These stars pack more mass than the Sun into a sphere barely 20 kilometers wide, and they spin with unimaginable speed, sometimes hundreds of times per second. That rapid rotation generates enormous centrifugal forces that help the neutron star resist the overwhelming pull of gravity. If it weren't spinning, the star's own mass might crush it further into a black hole. Thus, rotation literally allows such extreme objects to exist in a stable state. Even at the largest scales, spin contributes to order and coherence. Galaxies, those vast rotating islands of stars, maintain their graceful spiral structures because of their angular momentum. The stars within them orbit around a common center of gravity, their collective motion balancing the gravitational forces that would otherwise cause the galaxy to collapse inward. If galaxies didn't spin, they wouldn't have the time or structure to form stable disks and spiral arms. Instead, they would simply fall into themselves, forming dense, chaotic clusters. It's rotation that maintains the elegant balance between collapse and dispersal, keeping galaxies intact for billions of years. But spin doesn't just stabilize the shapes of celestial bodies, it stabilizes their orbits too. A spinning planet, for example, maintains a steady orientation in space thanks to a principle known as gyroscopic stability. You can see this in a spinning top. As long as it's spinning fast enough, it resists falling over. The same happens with planets. Earth's rotation acts like a giant gyroscope, helping to stabilize the tilt of its axis. This stability is what allows for relatively consistent seasons over long periods of time. Without it, Earth's axis could wobble chaotically, leading to extreme climate swings that would make life far more difficult. Spin even helps stabilize motion on smaller scales. The Moon's rotation, synchronized with its orbit, creates a delicate equilibrium known as tidal locking. It always shows the same face to Earth. This locking is the result of gravitational forces and rotational momentum reaching a state of balance. Similarly, in binary star systems, the stars often become tidally locked to each other, their rotations and orbits synchronized into an elegant and stable dance that can last billions of years. Rotation also helps maintain thermal and magnetic stability. For instance, Earth's spin contributes to the generation of its magnetic field through the motion of molten iron in its outer core, a process known as the geodynamo. That magnetic field shields our planet from harmful solar radiation, stabilizing the conditions necessary for life. The Sun's own rotation plays a similar role, driving its magnetic cycles and the patterns of solar activity that shape space weather throughout the solar system. From the smallest atomic particle to the grandest galaxy, spin acts as nature's stabilizing mechanism. It's the hidden scaffolding that keeps motion orderly, systems coherent, and energy balanced. Rotation transforms chaos into pattern, imbalance into symmetry. It's what allows the universe to evolve without falling apart under the weight of its own complexity. And perhaps the most profound thing about this stability is that it emerges from motion itself. In human experience, we often think of movement as instability, something that needs to be controlled or resisted. Yet the universe shows us the opposite truth. Motion is the foundation of balance. It's because planets spin that they remain steady, because galaxies rotate that they hold together, because stars turn that they shine consistently. Spin, then, is not just a force of change. It's a force of preservation. It's what gives the universe its shape, its rhythm, its longevity. Without it, everything would collapse into stillness and entropy, losing the harmony that defines the cosmos. With it, the universe becomes a living system of equilibrium and grace, where motion and stability coexist perfectly, each depending on the other. So the next time you look up at the stars or feel the subtle turning of the earth beneath your feet, remember that this endless spinning is not chaos, it's balance. It's the universe holding itself steady through motion, finding peace through movement, order through perpetual dance. As we bring our gaze back home, to our blue and turning Earth, it becomes clear that spin isn't just a grand cosmic phenomenon, it's personal. The rotation of our planet, this steady turning that we hardly notice as we live our daily lives, is not just a backdrop to existence, it's one of the fundamental reasons life exists at all. Spin gives us rhythm. It gives us stability. It gives us a world capable of nurturing and sustaining life in all its forms. Without Earth's rotation, our planet, and everything that calls it home, would be unimaginably different. Every moment of your life is defined by Earth's spin. Each sunrise, each sunset, each gentle transition from day to night is the direct result of our planet rotating once every 24 hours on its axis. That simple motion, so constant and unyielding, creates the cycle of light and darkness that shapes not only our perception of time, but also the biological rhythms of every living thing. From the opening of flowers at dawn to the sleeping patterns of animals and humans alike, the daily rotation of the planet has synchronized life into a universal heartbeat, a rhythm shared by oceans, forests, and even your own body. Earth's rotation is also what gives us the Coriolis effect, a subtle but powerful force that shapes global weather patterns. Because the planet spins, air and ocean currents are deflected, curving to the right in the northern hemisphere and to the left in the southern hemisphere. This effect drives the great circulations of air that create trade winds, monsoons, hurricanes, and jet streams. Without it, our atmosphere would move in simple, vertical motions, hot air rising at the equator and cold air sinking at the poles, with little of the complex variety that allows for global weather systems. The rotation of Earth transforms climate from monotony into motion, distributing heat and moisture around the planet and making it possible for ecosystems to thrive from the poles to the equator. Spin also gives us stability through tilt. The Earth's axis is not perfectly upright, it's tilted about 23.5 degrees. That tilt, combined with our planet's rotation, is what creates the seasons. As Earth spins while orbiting the Sun, different parts of the globe receive varying amounts of sunlight throughout the year. This subtle variation in light and temperature drives the cycles of growth and dormancy that define life on Earth. The rhythm of the seasons dictates migrations and plant life. It has even shaped human culture, agriculture, and spirituality. The tilt of our spinning world is, quite literally, the clock by which life measures its time. If Earth didn't spin, the consequences would be devastating. A non-rotating Earth would have one side eternally facing the Sun and the other trapped in perpetual night. The sunlit side would bake in endless heat, while the dark side would freeze in permanent cold. The thin band between them might be temperate enough for life, but even there, violent storms and atmospheric extremes would make the environment unstable. Our winds, tides, and ocean currents would vanish or behave unpredictably, and the delicate balance that moderates global temperature would collapse. The planet would no longer breathe. It would stagnate. Even the length of our days, another gift of rotation, plays a vital role in life's chemistry and evolution. The 24-hour day-night cycle has shaped the circadian rhythms of living organisms, influencing everything from metabolism and hormone production to behavior and sleep. Plants turn their leaves toward the rising sun, animals hunt and rest according to the shifting light, and humans have built their entire conception of time and civilization around the turning of our planet. Spin gives us not just physical stability, it gives us temporal stability, a regularity that allows for predictability, adaptation, and life's flourishing. Earth's rotation also interacts with the Moon in ways that further enhance habitability. The gravitational pull between the two creates tides, the slow, breathing pulse of our oceans. These tides, rising and falling each day, play a crucial role in coastal ecosystems, nutrient circulation, and even the evolution of life itself. Early life forms are thought to have adapted to the rhythmic ebb and flow of the tides, learning to live in cycles dictated by the spin of the Earth and its dance with the Moon. Over billions of years, this tidal interaction has also gradually slowed Earth's rotation and stabilized its axial tilt, preventing the wild, chaotic shifts that could otherwise destroy climates and ecosystems. Even our planet's magnetic field, generated by the spinning motion of molten iron in its outer core, owes its existence to Earth's rotation. This magnetic field acts as a shield, deflecting harmful solar radiation and cosmic rays that could strip away the atmosphere and make life impossible. Without spin, there would be no magnetic dynamo, and Earth's protective field would vanish. The solar wind would erode the atmosphere over time, just as it did on Mars, leaving our world barren and exposed. In this way, rotation doesn't just create balance, it safeguards it. And then, there's the poetic dimension of it all. The Earth's steady rotation connects us to the rhythm of the cosmos. Every sunrise is a turning toward the light, every sunset a turning away, a continual reminder that we are passengers on a spinning world, part of a universal choreography that has unfolded for billions of years. Ancient civilizations knew this intuitively. They built monuments aligned with the rising and setting sun. They celebrated solstices and equinoxes, and they marked the passage of time by the turning of the heavens. Humanity's first understanding of motion, time, and even mortality came from watching the sky change as the Earth spun. If the planet were motionless, the beauty of time would disappear. There would be no dawn or dusk, no seasons, no tides, no dynamic world of growth and renewal. The living Earth would lose its pulse. In a very real sense, life itself is a manifestation of spin, an expression of the universe's inherent motion. From the rotation of molecules within your cells to the turning of the planet beneath your feet, you are part of a continuum of motion that stretches from the quantum to the cosmic. So when you stand beneath the night sky and watch the stars appear to move across the heavens, remember, it isn't the stars that are moving, it's us. You are spinning with the Earth, orbiting with the Sun, circling through the Milky Way, all part of a cosmic dance that began before time itself. The gentle rotation of our world is not just a fact of physics, it's a miracle of balance, a perfect motion that makes existence possible. Without spin, Earth would be a silent, lifeless rock. With it, the world breathes, the oceans move, the winds sing, and life endures. Every living thing on this planet owes its existence to that ancient, unending motion. The universe spins, and because it spins, we are here to witness it. From the tiniest, invisible particle to the largest galaxy spanning hundreds of thousands of light years, everything spins. Every atom, every planet, every star, every cluster of galaxies is caught in an endless, graceful motion. The universe does not stand still, it dances. This spinning, this rhythm of motion, is not some secondary feature of reality. It's the very pulse of existence, the heartbeat of the cosmos itself. Think about what that means. Every second of your life, you are spinning along with the Earth, orbiting the Sun, swirling through the Milky Way, and moving through an expanding universe that has been in motion for 13.8 billion years. The energy that drives this motion, the angular momentum that began in that first luminous instant of the Big Bang, still flows through you. The atoms that make up your body spin just as the galaxies do. The same fundamental forces that shape the stars are humming within your cells. You are, quite literally, made of the motion of the universe. It's easy to think of spinning as something ordinary, as though it's simply the way things move. But when you really pause to see it, spin becomes something far deeper. It's a universal act of balance, creation, and persistence. Every turn of a planet keeps it stable. Every rotation of a star keeps it shining. Every orbit of a galaxy keeps it bound together. Motion is how the universe holds itself in harmony. Without it, there would be no structure, no order, no light. The universe spins because that's how it sustains its existence. It's how it breathes. And that motion connects everything. The spin of an electron, the orbit of the moon, the rotation of the Milky Way, they are all echoes of one another, repeating across scales, bound by the same unbreakable laws. Each spin is a note in the cosmic symphony, resonating in perfect mathematical and physical harmony. When you trace that motion backward through time, it all leads to the same origin, that first cosmic impulse, when the universe itself began to expand and turn, setting in motion everything that would ever exist. But what's perhaps most beautiful is that this cosmic motion is not random chaos. It's ordered, elegant, and deeply meaningful. Motion gives rise to pattern. Pattern gives rise to form. Form gives rise to life. Without the eternal turning of the universe, there would be no stars to light the night, no planets to harbor life, no tides to nurture the first living organisms, and no rhythm by which life could measure its days. Everything we see, everything we feel, everything we are, comes from motion. The universe is not a static sculpture. It's a living, breathing dance of energy and matter in perfect perpetual motion. When you look up at the stars, you are not just witnessing the distant past. You are witnessing movement frozen in time. The light that reaches your eyes has traveled across the spinning fabric of space for thousands or millions of years, carrying with it the story of the universe's eternal dance. That light, spun, bent, and stretched by the rotation of galaxies and the warping of space-time, connects you to the farthest reaches of existence. You are part of that same motion. You have always been. In the end, the universe teaches us something profound through its endless spinning. Stillness is an illusion. Even in what appears to be silence or calm, there is always motion. Atoms vibrating, planets turning, stars pulsing, galaxies swirling. The cosmos is never at rest because it is motion through and through. The moment the universe stops moving would be the moment it ceases to exist. Spin is not a feature of creation. It is creation, unfolding endlessly, beautifully, everywhere. So, as you sit here on this spinning planet, racing through space at unimaginable speed, take a moment to feel that motion. The sunrise that greets you, the winds that move the trees, the heartbeat in your chest, all are part of the same universal rhythm. You are part of the cosmic dance. You are made of movement, of energy, of spin. From the smallest subatomic particle to the largest spiral galaxy, everything turns in harmony with everything else. The same physics that keeps a skater spinning on ice keeps galaxies in rotation across the heavens. The same angular momentum that stabilizes planets gives electrons their behavior in atoms. The same laws that guided the birth of stars govern the orbits of moons and the movement of life on Earth. The next time you look up at the night sky, don't just see stars. See motion. See the slow, patient turning of the cosmos. See a universe that refuses to stand still, that transforms every ounce of chaos into rhythm, every collapse into spin, every silence into music. See a creation that endures not because it resists change, but because it is change. Everything spins, everything moves, everything flows. The universe, from beginning to end, is a dance of motion, and you are a dancer in it. Every breath you take, every second that passes, every thought that crosses your mind happens because the universe keeps turning. The cosmos doesn't rest, it dances. And in that eternal dance, we find the most beautiful truth of all, that to exist is to move, and to move is to live. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. like the video and subscribe to the channel for more such amazing videos.